Today we're going to see some special topic regarding problems that we have with models. When you model something and you connect it a certain way, there's no guarantee that you're going to get a set of explicit equations. And the problem is that you might have specified too many elements, or you specify not enough elements, or you might have specified a redundant element. So you don't know until you're trying to write the equations, and if you intend to connect it a certain way, you also don't know whether the equations will come out right. This is particularly true and obvious in electrical systems because we can't predict exactly how the equations are going to come out just by looking at the circuit. A mechanical system might be a little bit more obvious, but it's important to understand when you get one of these difficulties, what does exactly physically mean. And that's the intent of this presentation, is to show you how, in this case, you can see in there, when you get derivative form, derivative causality, why does that happen and what is the solution? So let's take a look. Let me give you an outline of what I want to say. I'll give you an introduction, which I did, an understanding of how derivative causality occurs. What is the physical meaning or elimination of derivative causality? If you have dependent elements, which are the cause of derivative forms, can you combine them? Or can you actually introduce other elements that would help you solve this problem? I also I'm giving you here the derivative causality detection by using CAMG, and how you could actually produce the differential form, which is what we have, and then how do you actually combine things to produce explicit state space form. And then finally, what's the CAMG solution on the relation to physical reality. Then we'll talk about the multi-elements in derivative form, and I will finally touch on the CAMG Simulink solution. Okay, because we're mechanical engineers, we like this kind of systems. I am putting here a system that is before you, a system that deals with the valve mechanism and rocker arm on an internal combustion engine, so that you can locate yourselves. This is the way the intake and the exhaust valve on engines work. All right. What you have is a push rod in here, whose objective is to create a motion this way. And there is a rocker arm in here which is pivoted here, which objective is to rock this back and forth, and therefore push this valve stem down. And if you do that, you see the airflow or the air plus the mixture of gasoline and air comes in here, and you let into the combustion chamber. When this is on the closed loop position as it is right now, these two things are not touching, and the spring is pushing this up, and so this push rod is connected to the camshaft, and this camshaft rotates, and by the rotating motion pushes this up and down, and this of course produces the motion. So if you do a model of this, the drawing on the right hand side would be a reasonable model. See here, there is the valve right there with some spring and damping. Yeah. And then there is the connection of this that has also a spring and damping to the connecting rod, which in this case is modeled as this beam. Do you see? This is this. Okay. And then on this other side, you have the connecting rod, which in this case we model it as a spring and a damper. Then you have the push rod, the mass itself, and that is connected also with the spring and damping to this tappet, and that one has a spring and damping connecting to this lobe, to the cam. So the question is our model detailed enough? Is it correct, or is it over-specified, or is under-specified? That's the question. So in order to answer that question, we transform the model that we have into a bond graph model over here. Let's examine whether that transformation is, how do we do it? Obviously, you could see here that I did not start my explanation by saying put the ones here and then do the connections. But if you're doing it and you're studying this, I highly recommend you do that, because that is the way we obtain this graph. So if we review that, you will have that you have a rotation in here, so that's a 1. You have this point and this point, those 2 points are 1s, and this TF is representing obviously this beam, but in here we put another one for this and another one on the other side. Those are these 2. You have another one in here, that's this one, and then you have one with the input over here. And so this set is this set is that, this set is this one, this set is this one, and this set is this one. So as you can see, this is a more significant model than what we have done in the past. So in here we're gonna say, okay, I finally have my bond graph model. Now you see on this example, for you that you understand bond graphs, we might not need this detailed explanation. However, just to make sure everybody in the whole world understands, you can put labels to all the variables, like C3 is the elastic deflection, C11 and C29 is the bending deflection. You have the helical spring stiffness, the mass of the tappet, the push rod, the mass moment of inertia of the rocket arm, mass of the valve. This is the rocket arm is divided in 2 parts, left and right, and that way we can consider that. And in the middle you have the rotational inertia. SF1 is the cam follower input, and SF35 is the valve motion input. Okay. From the first representation, this one, see how I represent it here? I am going to idealize and do it this way. In other words, let's say now you say, you know, the first one, the rocket arm was a lever, and that's the, you know, it's very obvious. But how about if I say, you know, maybe it's not a lever, I'm just gonna model it with two masses concentrated at each end. Okay, sounds reasonable too, right? If you do that and you follow the steps that I have shown you to create a bond graph model, you will have this in here and this over here. And when you assign the causal marks, this one on the right hand side is not going to complete right. This has happened in other examples that we have seen throughout the semester, but I have been waiting until now to dedicate some time to address them, specifically what the answer is. Okay, so you have in here, this is one problem, and that's exactly what I'm trying to do here today, is to resolve it. Let me put this back again. Remember, this is a different interpretation of what we had over here. Yeah? And so if I do it this way, I get this problem. But by the same talk, that instead of being two masses, you could combine the two and the inertial effect be one mass, but with a combined effect. Then what you end up happening is you have this kind of thing. See, now you don't have this one, but the model that you have should be equivalent to the previous one. So what I have done is I suppress this one over here, but then I have to modify the inertia on the other side to be able to keep the system correctly, as it really should. You know, it would have been easier to do it with the first example that I have, but because I am trying to explain to you why this happens, the first conclusion on this one is that, you see, you cannot have it this way. It's not two inertias, but one, because what happens is this one is depending on the motion of the other. That's why. And that's why derivative causality happens, is when one element, by the way you connected it, you made it dependent on the motion of the other. So the two are not going to produce independent differential equations. That's the problem. Mathematically, that's what the problem is. You end up with one of these derivative forms is saying the equation of that one that is in derivative has to be function of the others. It's a dependent element. And as you can see that I created that by making the assumption there were two, when in reality we could reduce it to one, but with the equivalent inertia of this. Just so that I can get my point across, let me give another example of this. Let's say you have an electrical motor. You know that the electrical motors have a armature inside, right? Big rotating armature. Should we consider the inertia of that when we model the motor? Of course, I think that is very obvious that we should do that. But the motor shaft is connected to a flywheel or a gear or some sort that you are driving. Now you can see the problem. If you model the armature of the rotating motor plus the flywheel as two separate parts, you're going to have this problem. Because you see there, you clearly see in the case that I'm telling you, the armature, if the armature rotates, so does the flywheel, right? And because they are connected together, wouldn't it make sense more to consider both of them as one? I think it would, because if you don't do that, then you're going to have one inertia depends on the motion of the other. I think that's probably the best practical example I can give you, is a motor with a flywheel. If you consider the inertia of the motor and the flywheel together, you are home free. No problem. If you say, oh, these are two separate parts and they are rigidly connected together, then you'll have this problem. If you say, however, there are two different parts, but the shaft that connects the two of them bends a little bit, then you're okay again. The only trouble with that is you have introduced a high stiffness element, because you don't want a wobbly shaft. It has to be stiff. What does that mean for the computer? It means that by introducing high stiffness element, you solve the dependency of the mathematical problem that you had, but you created a challenge for the computer simulation, because high stiffness elements will require that the computer do very small steps of integration. So your simulation will slow down, but you get the answer correctly. Okay, so that's where we are with that. But I thought I'll keep working on this. In order to do what I just did, remember I said instead of considering it like this, I am going to do it like this. Well, this is not arbitrary. You have to have some mathematical basis for doing that. And the way we do it is by equivalent the same kinetic energy. Like the kinetic energy of the on this side should be the same as the other side. We have a velocity ratio in there. And then if mass B is placed at an equivalent mass at A, then the mass at A has to be the mass at A is mass A plus B over A square mass B. So the value of this has the other one combined with this geometry. It's, when you study calculus, I think you must, I'm sure you came across this equivalent inertias. Look, if you put it into Chem G, the first way was, do you see the derivative form right there? See? And you know this is going to have problems. But if you suppress that and you change it to this, then you won't. The only thing is you gotta do is make sure the I-27, the value is like this. Okay. Now let's say let's try for the sake of example, I am going to try this simple example as if we have a transformer with a dependent on one side. Now I want to go from the complex example that we had to a simple example in order to explain you mathematical foundation for this. And in here, do you see, if we produce the equations, the individual equations like this, you produce two of those equations that are funny, because E6 is dp sub 6. Do you see, when do you see dp's on the right hand side? That's not cool, because it means that the derivatives dq3 and dq8 are fine, but the derivative on the right hand side is caused by this derivative causality. So we really have a major challenge now, that the derivatives, instead of ended up on the left hand side where you can calculate, you need to evaluate the derivative first on the right hand side to do the others, because we know it's a dependent derivative. So that's not helpful, to get one of these on this side. You can derive the equations, but you have a mathematical problem. MATLAB and Simulink have these implicit solvers that they would actually find a solution, a mathematical solution for this, a numerical mathematical. So that's one way of solving it, but doesn't mean this is the most efficient way. Now, you see, if we write them into the Cauchy form, which by now you know what it is, we have actually replaced all the e's and f's, and we only have the derivative form. If you do that for this example, you are going to end up with these three equations and this one on the right hand side. Not cool. So in order to solve this impasse, you need to find another equation for this by hand. But that one, do you see, if you find out this is going to have dp1. So you begin doing something like this and you're in a never-ending circle. When I worked for IBM, I think it was the first week I was there, they gave me one of these problems, the circuit, that they said, well, we don't know what's wrong with this. I mean, if we keep going here and the equations don't come out right. And when I did the Von Graph model of this, I recognized this is, you have a derivative form or an algebraic loop, and that's how you resolve it. In here you see, I am going to propose something. We need to find some way to transform these equations that we have it in this not so nice form to ones that are in the nice form. So here's the idea. Do you remember that state space form has this format? And that's what Von Graph produces, especially in CAMGSYM. That's exactly what it does. But you see, in here, you have first the normal ones, and then you have this dependent one, and you have it in such a way that you can resolve it. So here's what I did, and here's what I propose. Let's just do the minimum on this. The minimum. All I did is let's just represent the system as it's in here, and we are going every term. You see, A and B is the normal one. Every term that has the dependencies, we're going to call it E. And this is this x dot of derivatives. We need some x dot derivatives in terms of the you know, of the others. So this whole thing is funny, because you see, you have these derivatives on the right hand side, and up to now you can't solve it. But here's I spent quite a few weeks thinking about how to do it. This solution, I found it a few years ago, so it's not this week. I already tested and published this work in a conference many years ago. So here's the idea. This is our mathematical problem, right? I said, okay, if this is the case, we're starting over here. We could put this into here, see? And if you do this, you have this equation. And because we want them in explicit form, we could move this term to the other side and obtain what we have in here. But if I take the inverse of this factor here, if I take the inverse of this, I would actually produce the nice form that we want. Sometimes you have to you have to do it that way. You have to produce new matrices. So I said I produce one A new and one B new, and we will have to produce one C and D as well. See? So this is the new A, this is the new B. So even having the derivative form on the right hand side and putting it in this form, by doing a matrix inversion with this matrix product, voila, we solved the thing. But you see, this slide that I'm showing you now shows you the mathematical side of doing such a thing. But the picture here showed you, if you take this one off and move it to the other side, show you the physical aspect of it. So I wanted to do this. You see the derivative form. I got this out of the ChemG software. And then I actually did exactly what, because MATLAB is very good at working with matrices, I obtained my new A, see? And that means now I don't have it in here. And then I put it over here, see? And then we don't have problems with derivative causality anymore. Now if you want to put an equivalent mass on the other side, this is the same thing, see? So I said I am gonna keep causing trouble here, because I wanted you to see physically the changes you can make to a system, and you can mess it up very easily. See what I have done now? We connected the two masses as if the push rod would be a rigid body. No spring or damping at all. And you can say, well, you know, that's really closer to reality, because the push rod is a push rod. It's not spring. Well, yes, that's true. But be prepared. If we do this, see, I have done it in the I have done it here, and I did it over here. And I had it like this too. 3 elements in derivative form. Now we really have a little nightmare, because now we have 3 elements in derivative form. The equations are not going to come out, they're going to be dependent. See? So I think what we need to do is to is to find a solution as I have proposed, either by mathematical matrix inversion, or you could solve it. Let's see, right there is, I put it into CAMG and it shows 1, 2, 3, 4 elements in derivative form. We've never done a problem like this in this class. Maximum we had 1. But now that we are talking about a full-fledged solution, then okay, these are the equations for this ones that has 4 derivative forms. So this is the part that don't have problems, and then there are the ones that do. See, on the right hand side you have dq, dp30, dp27. So we have derivatives on the right hand side. So it's 27, 30, 3 and 9. Where is the derivative on 9? Yeah. Okay. So we have this form. Yeah. And what happens is if you combine these two into one, and you combine these two into one, you will have the in other words, this inertia is going to see this you combine the effects, and so you eliminate the elements in derivative form. You will end up with a much more complex matrix, but so what? The computer is the one doing it. And so in here, this is the solution for multi elements in derivative form. In this case, you have the new A is I minus E times F inverse times A. This is the B matrix. Obviously it gets a little more complex, but same way I calculate the new B. And I have solved this. You will do the same thing for the C and the T matrices. Okay, let's take a look a little bit about the CAMG Simulink solution. You have this element that I have in this problem. If you click into the one of the elements, displays you the CAMG solution. In this particular case, when you have derivative forms, you could represent this whole thing into Simulink. You see? What I'm trying to say is that you could have a Simulink model with derivative form. And actually, once you do it this way, you could solve it, because Simulink has implicit solver of the differential equations. So I think that is a solution. So you begin to see why, and before we didn't want to deal with this because it's involved. But it's not like it's impossible. You just need a little more work and knowing exactly what you're doing. But this is an option. I'll just put all those in Simulink and let the Simulink hash with it, you know, and then it should work. This is the Simulink model from the bond graph. And then this is the same thing as if I would have done this. So this is there's one way, but you could produce the Simulink derivative form and then of course it does it in the whole block diagram. That's what these are. See, all these gains are big because of the equation. They come from here, from these equations right here. Remember, all Simulink is a graphical representation of the model in integral or derivative form. So my feeling is, and the lesson for this is that maybe even this one is a little bit risky in the sense that there might be some numerical instability or so, and then but the best way that I suggest is to combine elements, combine them together. I think I have a slide of the combined elements. Yeah, here. See, equivalent one. So you go and change this, not just by erasing them, but by making this equivalency. Or like I said, once you have the equations like this, you can go into the Simulink model and solve it as well.